Good morning, ladies and gentlemen. My name is Artur Gańcza, and together with Maciej Niedźwiecki and Marcin Ciołek, I am an author of the article describing the pre-estimation technique and its application to identification of non-stationary systems. Let me start by defining the problem that we are trying to solve in our article. So consider a non-stationary stochastic finite impulse response system governed by this equation, where t is a discrete time, phi is a regression vector made up of the previous values of the input signal, which is a locally white-sense stationary sequence. E denotes white measurement noise, and theta is a vector of unknown time-varying parameters. The goal is, of course, to estimate those parameter trajectories based on the available input-output data. There exist different approaches to this problem, which can be particularly challenging when no a priori knowledge about the parameter changes is available. It may also happen that not only the speed of parameter changes is unknown, but it also varies in time. Just like in the example shown here, in which we can observe the evolving speed of parameter changes. One approach would be to assume that locally, inside some analysis window, system parameter changes can be approximated by a linear combination of linearly independent functions of time, the so-called basis functions. Then we solve the problem of identification of a higher order but locally stationary model using, for example, the least squares technique. When the obtained parameter estimates are used to describe system dynamics at time instant t only, which corresponds to the sliding analysis window technique, the procedure is called the local basis function method. It is worth noting that this procedure is quite computationally demanding because of the number of hyperparameters, and the results that are similar to those yielded by the LBF method can be obtained via a two-step procedure consisting of pre-estimation and post-filtration. It is easy to check that the pre-estimates defined like this are unbiased, regardless of the type and speed of parameter variation, but they are also very noisy. So in order to achieve a satisfactory bias variance trade-off, additional filtration is performed. When the impulse response of the post-filter is chosen, as in this slide, the obtained method can be seen as a fast version of the local basis function algorithm, the FLBF. Note that the FLBF approach reformulates the problem of identification of a time-varying system as a problem of smoothing of system parameter pre-estimates. Here on the left, we can see the figures showing the LBF estimates drawn with a black line superimposed on the true parameter trajectories, which are red lines, while on the right, we can see the FLBF estimates obtained for the indirect pre-estimates, which we'll be discussing in a while. As we can see, both results are almost indistinguishable, while the computational cost of the FLBF method is significantly lower. Computation of the pre-estimates requires the knowledge of the true covariance matrix of the regression vector, which is not always available or may slowly change with time. So the easiest solution is to replace the true covariance matrix with its approximation obtained using the exponential weighting technique. Please note that the inverse of this matrix can be computed recursively using the well-known Sherman-Morrison formula. Additionally, under some pretty general assumptions, it holds that as the forgetting constant tends to 1, the approximation of the covariance matrix tends to its true value in a mean square sense. Moreover, the direct pre-estimates are still approximately unbiased. The other way of computing the pre-estimates is by the inverse filtration of exponentially weighted least squares estimates, which allows one to approximate the whole expression for the pre-estimates, not only the value of the covariance matrix. And it is straightforward to check that those indirect pre-estimates are also approximately unbiased. It's interesting to look at the difference between these two ways of computing the pre-estimates. It turns out that there is in fact a meaningful difference. Black lines show the pre-estimates, while the red line is the true parameter trajectory. And on the left, we can see direct pre-estimates. On the right, indirect ones. In both cases, the value of the forgetting constant was set to 0.9. To understand the source of these differences, we should take a closer look at the pre-estimation errors. These errors are made up of two components, and note that while in the case of direct pre-estimates, the first component depends on the true parameter trajectories. In the case of the indirect pre-estimates, we have the difference between true parameter trajectories and their EWS estimates from the previous moment of time. Since typically the norm of this component is much smaller than the norm of this one, we can expect the indirect pre-estimates to be less noisy. It is clear that for the FLBF method, it is more beneficial to use the indirect pre-estimates. However, the important question which still remains is how to choose the number of basis functions and the length of analysis interval for the post-filtration procedure. This question is of crucial importance because, as shown in the displayed figures, when we decrease the number of basis functions and increase the length of analysis window, the estimation variance decreases, but the bias rises. The opposite effect can be observed when we increase M and decrease K. In our article, we propose a method for adaptive choice of these two hyperparameters based on a leave one out cross-validation approach. We also show that this allows one to achieve a satisfactory bias variance trade-off. In fact, there is a way to further improve the quality of pre-estimates. If we have the system parameter estimates that are more accurate than the EWS estimates, we can apply a special enhancement procedure to reduce the first component of the pre-estimation errors. Note that if our estimates are very close to the true parameter trajectories, then those two components will approximately cancel, and we will be left with something very close to the true parameter trajectory plus some additional noise. It is also worth noting that those enhanced pre-estimates can be easily computed using the adaptive FLBF estimates and direct pre-estimates. It is also easy to show that they are approximately unbiased. Summarizing, to obtain the enhanced pre-estimates, we first compute both indirect and direct pre-estimates. Then we perform adaptive smoothing of the indirect pre-estimates. Then we use the adaptive FLBF estimates and direct pre-estimates to compute enhanced pre-estimates. And finally, we again perform the adaptive filtration of enhanced pre-estimates. And when we compare the indirect pre-estimates on the left with the enhanced pre-estimates, we can observe the significant variance reduction. This reduction follows from the fact that the norm of this element is typically lower than the norm of this one because of the lower estimation accuracy of the EWS estimates compared with the FLBF estimates. To verify the statement, we simulated a two-tap FIR system described by this equation. As the input signal, we used an autoregressive process, and the parameter trajectories are portrayed here in these figures. Then we performed analysis for 100 independent realizations of the measurement noise. And as we can see, the adaptive procedure always yields results that are better than the best of the results for the estimators incorporated in the parallel scheme. We can also observe that the smoothing of the enhanced pre-estimates improves the results in all cases and sometimes gives even better results than those obtained for the original LBF approach. In the article, we provide additional examples for different SNRs and speeds of parameter variations. Summarizing, the problem of identification of a non-stationary stochastic system was considered and solved using the time-localized variant of the basis function approach. The approximate solution as an alternative for LBF is based on a post-filtration of the pre-estimated system trajectories. For the polynomial basis, FLBF and LBF estimators are recursively computable. Two important design parameters of LBF estimators can be selected in an adaptive database-dependent fashion. And the proposed scheme of smoothing the enhanced pre-estimates proves to yield results that are either better or only slightly inferior to those provided by smoothing of indirect pre-estimates. Thank you for your attention.